Okay, so if we see anything dealing with variables that looks like a rational function, we always are thinking that we want to do power rule. But there's one instance where power rule doesn't quite fit because let's say we try power rule for this problem. So 1 over x. If we try to bring that x up to the top, this becomes x to the negative 1. And what happens if we try to do power rule with this particular exponent? This becomes what? X to the what? We add 1 to the exponent, right? So what does the new exponent turn into? 0. But then we put in the denominator what? 0. Can we divide by 0? Can't. So normally, any other power would allow power rule to work. If it's 1/2, negative 1/3, 1/4, negative 2, right? Any power can work, but there's one instance where it fails, and we have a special rule for this one particular exception. So it relates to natural log. So if we think back on first semester, the derivative for natural log of u is u prime over u. And essentially, the u prime over u is in the form of 1 over x dx. And so if we undo this u prime over u, it becomes natural log absolute value of u. So that's the rule that we're going to be using. The integral of 1 over u du is natural log absolute value of u plus c. Now, the danger of this is that as we get more comfortable with this form, I think our natural tendency is we're going to assume that every variable in the denominator is going to be natural log, but it's only if it's 1 over u to the first power, right? If it's 1 over u to the second power, if it's 1 over u to the 1/2 power, we still bring it up, we still go through a power rule. Okay. So we only use this natural log rule if it's integral of 1 over u to the first power. Okay. So let's look at example 1, and let's go down our list of priorities here, or our list of steps. Anytime we see integral problem, we always are asking ourselves, can we just split up into individual fractions and rely on splitting up and power rule? But we see that as soon as we see multiple terms added or subtracted in the denominator, we know we can't split up into individual fractions. If it was 2x over x squared, then we would want to think about just relying on power rule. But this is x squared plus 1. We're stuck, not being able to expand. So our next option is looking for u substitution. And a good u value would be the entire denominator. Normally, we're looking for a set of parentheses, but here we also want to consider, the possibility of letting the u value be large enough where it could potentially take up the entire denominator. So let's see what happens. If our u value is x squared plus 1, du over dx, okay, power rule, right? Cross multiply. We can replace the x squared plus 1 with u. Dx becomes du over 2x. We get the 2's to cancel out. And the x's to cancel out. So everything goes away. But the important thing is the x's do go away. And then all we're left with is 1 over u to the first power. Careful there, first power. Again, if it's any other power, we got to bring it up and go through power rule, but it's u to the first power. So this fits our natural log rule. So our rule is just natural log absolute value of u plus c. And then finally, if you're going through u substitution, you want to bring back your x variable. Okay, example 2, 1 over x ln x. This is a little too complicated for any one rule to handle. We don't have and also these are being multiplied. We can't say, okay, we'll do 1 over x and then we'll do a separate rule for natural log of x. So we know we got to go through u substitution, but there are a couple of options where what the u value could be. Let me list out those options. Maybe the u value is x. Maybe the u value is x natural log of x. Or maybe the u value is natural log of x. But only one of these is going to allow us to move forward and allow things to work out. We talked about how we never want to do a 1-for-1 substitution, right? If you do a 1-for-1 substitution, yes, you're converting your problem in terms of u, but you haven't changed the problem. You're just making a different variable with the same problem. So we know we're never going to do a u substitution with just x. If we let u value be x natural log of x, what would the derivative produce? Or what would you have to do to produce the derivative, or to do du over dx? These are two separate terms here. We would have to go through what to find the derivative? Product rule. And if we went through product rule, there's going to be a whole big mess of terms, and we don't see anything else that could potentially pair up with this x ln x, right? If this whole thing is the u value, there's no other variable that's going to match this derivative. So we know that this is too much. So let's see if natural log of x can allow us to produce something that will get all the remaining x to go away. So here, our natural log of x is our derivative, du over dx. First semester, our natural log of u's derivative is u prime over u, so 1 over x. Cross multiply. Natural log gets replaced with u, dx is replaced with x du. X's cancel out. Okay, 1 over u du, this is u to the first power. This matches perfectly with our natural log rule. So we go ahead and apply that. Natural log absolute value of u plus c. And then don't forget, bring back your original x variable. Looks a little bit strange here with natural log inside of natural log, but Okay, example 3, I want us to change the denominator here. Make it x plus 1. The other problem with the x squared plus 1 is something that requires long division, but I just haven't seen any long division on AP exams in a long time, and I just don't think it's. I just want to just teach what I think is the has the higher chance of showing up, and that is using synthetic division. Now, we could also use long division here, but synthetic division is faster, it's more efficient. We just have to practice the steps to get to it. So example 3 is one where you're looking at the problem and you're thinking, okay, well, first off, we can't split up because there's too many terms. If it was just divided by x, then we can split up into individual fractions, separate into 3 separate fractions, and then clean up and then apply either power rule or natural log. But as soon as we have terms that are added in the denominator, you know that it's hard to split up. So then the next option is, well, what about U substitution? U substitution is going to be a better fit if the denominator is a higher degree than the numerator, because when you go through a derivative, typically it's the numerator that has easier time canceling out. So the fact that the numerator is higher than the denominator is causing an issue where no matter what U value we select, we're not able to get the other side to cancel out. And there's a certain look to these types of problems where the numerator is either higher or the same as the denominator, and there's like x plus 1 or x minus 3 or 5 minus x. Kind of gives it away that this is a synthetic division problem. So synthetic division problem, first off, there are no fractional exponents. Okay, if you see fractional exponents, you know it can't be synthetic division. So synthetic division has a certain look to it where it's like x plus 1 or x plus 3 in the denominator, and all the exponents are a nice integer value, positive integer value, like x cubed plus 2x squared plus 3x, right? Has this certain look to it. So synthetic division allows us to rewrite the problem. In an easier form. So when you go through synthetic division, you want to make sure that you don't just stop there, right? Because all we've done, if you go through this process, is we've created a different version of the problem, but we still have to go through the calculus step. So what we do is we set the denominator equal 0, and we find the critical point. And then you're going to take that number, -1, and then you're going to put a half box. And you're just going to put the coefficients of the numbers in front of the x's. Okay, so don't put x squared, x, and 1. Put 1 for x squared, 1 for x, and 1 for the constant. If there's a degree that's skipped over, let's say if it was x squared plus 1, then you would have a placeholder for that x variable, and you'll call it 0. But here, there are no variables that got skipped over, so we start 1 represents degree 2, this other one represents degree 1, and this one represents the constant. Okay, so there's a place for each degree. So the first step is we're going to always bring the first number down below the line. Okay. Next up, you're going to take the factor that you have out here, multiply that with the number below the line. What's -1 times 1? Just -1. So you're going to put that number in the second column, and then you're going to add. 1 minus 1 is 0. Okay. Multiply with this number again. -1 times 0 is 0. And then 1 plus 0 is 1. Now, if this number is anything but a 0, then we call this the remainder. This is the leftover term. And the remainder tells us that we can't divide any further, so we're just basically having to have some leftover in our problem. Now, we're dividing x squared by x, essentially. So all of our degrees will fall by 1. So what was x squared will now become x. And once you have that starting degree, then everything else falls by 1. So this is degree 1. This is a constant. And this is the remainder. So the way you write the remainder is you're going to put it over the x plus 1 because you're indicating that I can't divide any further. I've divided as much as I could, but this is the leftover term. Now, once you're here, we're still having to do our integral process. But now the nice thing is that we're basically able to split up into individual fractions and basically into individual problems. And now we have an easier, these are basically the same problem, but it's a lot easier thinking about this as 2 separate problems than one extended, connected, difficult problem. So 1x, that's just power rule. That's just x squared over 2. Now this 1 over x plus 1 is going to be its own u substitution, but I just want to show you that it's going to be a pretty quick u substitution problem. And then once you get comfortable enough with this type of problem, you can maybe even skip the u substitution because you already know what's going to come up. So if the u value is x plus 1, du dx is 1, dx equals du. So this ends up being 1 over u du. And this, we know that 1 over u du is natural log absolute value of u. And then replace the u back in terms of x. So this just becomes natural log absolute value of x plus 1 plus c. So if you ever see like a coefficient, a linear term where it's only x plus 1 or x minus 3 or x plus 5, and there's a constant above, you could just jump directly from here to here and just skip the u substitution portion. But whenever you go through synthetic division, you're going to be expecting some natural log to show up at the end. Okay, next page. We have some more specific integral rules that do not fit the original set of integral rules, trig rules that we learned. So remember the original 6 that we learned. We have the integral rule for cosine, for sine, for secant squared, for cosecant squared, for secant tangent, and for cosecant tangent. But we don't have rules for tangent, cotangent, secant, and cosecant. Right? Those were not from the original 6 derivative rules. So these special rules are involving natural log. So tangent's antiderivative is just negative natural log, cosine of x plus c. And then cotangent's antiderivative is just natural log absolute value of sine of x plus c. There's a certain way to help remember these a little bit easier to go through u substitution, but I think I want to come back to that a little bit later. But these are our additional new trig rules that does not fit the original 6 that we've learned from the quizzes from the last unit. Okay, example 5. Let's do another synthetic division. So I'm not going to do long division. So synthetic division, I'm not going to say this is a synthetic division problem. It's more like we have to be able to recognize, especially if there's multiple terms above, and then you have like x plus 5 or x minus 1 or x plus 2 below. That's the indication. There's a certain look to how synthetic division kind of presents itself. So we start off by finding that factor. So always the opposite sign, because we're always setting our denominator equal to 0. So we start off with -5, half bracket. Now we have 1 to represent x cubed. What's the next number that we need to put? 0, because we don't have anything for x squared, but we still have to make sure that there's a place for x squared. So technically this is x cubed plus 0x squared minus 6x minus 20. Okay. So first thing, always bring the first number down below the line. Okay. Multiply. -5 times 1 is -5. Add. Multiply. Add. Multiply. -95. And then add again. So these numbers are a little bit large here. -115. Now we started with x cubed, but we're dividing by x. So what degree are we going to start here with? X squared. So you're always going to start at a degree lower than your numerator. And then every degree is going to fall by 1. So next one is 5x. The next one is a constant. And the last one is the what? What do we call this? Remainder. So remainder means this is a leftover. If this is a 0, then there will be no remainder. But there's a remainder, and remainder over the x plus 5 is indicating that we can't divide any further. This is the leftover that will not divide out evenly. So remember that this is not the solution. This is just an easier version of the problem. We've just rewritten the original problem, but we're now able to split up this fraction into multiple individual standalone terms. And typically the way these synthetic division problems are going to look, it's always going to be the first few terms are all going to be power rule. And the last term, it's just going to be a simple use substitution that will lead you directly to natural log. So a lot of times we can skip the natural log, the use substitution process, because you know that this u value will just produce a derivative of 1 and ends up being 1 over u with the coefficient in front. So power rule, x cubed over 3. 5x squared over 2, 19x. And this is basically 115 is the coefficient, and natural log s value of x plus 5 plus c, because this ends up being 1 over u du. So I think it's just easier if we recognize this as natural log and just jump directly to this without having to go through a full use substitution. Okay, your homework is pages 1 and 2 on the packet. So first off, sorry, I'm in the process of changing all the chapter numbers. I'm still doing a little bit of the previous chapter naming, or the previous book. So the previous book was chapter 5, and the new book is chapter 7. So I'm still trying to get that all lined up. So for now, just know that there's a mismatch in numbers here. But under your homework packet, your homework is just pages 1 and 2. And then there's one problem that doesn't that I realize is not fitting for our homework. So if you can cross off number 19 and replace it with number 18. Here's number 18. integral of x cubed minus 6x minus 20 over x plus 5 dx. So I'll send a reminder this afternoon, and I'll also send you a link to the key so you can check your answers. All the solutions worked out. Oh, and then we didn't quite go over these, but yeah, just keep in mind on page 2, these are definite integrals. So we talked about how with definite integrals, you're going to basically ignore the bounds at the beginning, right? You're going to go through your full use substitution process, and the very end, bring back your x, and then after you bring back your x, then do half bracket, then plug in your upper and lower bound. So we didn't go over that, but it's the same process with the definite integrals. Any questions? Homework? All right, let's go back and do some more test review. We got through most of page 6. But again, I want to highlight how similar F, G, and J are. Because so if you can, I don't know if I asked you to do this yesterday, but if you can put a star next to F, G, and J, and just see that distinction between the three of them, they all involve integrals, but they're all a little bit different from each other. So total displacement is just a definite integral, no absolute value. We're not adding anything to it. Total distance is just the integral with the absolute value. But then if I'm looking for a specific location, then it's going to be final equals initial plus displacement. Yeah. So I see students want to do this. They want to add initial position to total distance or initial position to total displacement. But that's only if I'm asking you to find a physical location like x of 4 or x of 3 or x of 9. So that's when you do initial plus displacement. So put a star next to these and make sure that you can distinguish between the three of them. Okay, we're going to skip L and look at K. So K says find the average velocity. So average velocity, that reminds us of average value. So we're going to find the average value of velocity. So f of c is equal to 1 over b minus a, integral from a to b of v of t. Our a and b values are 0 and 4, so we can just get that 1/4. And just plug this in our calculator. Now we can just carry this number down if we want to, or we can just do the process again, do math 9, integral from 0 to 4 of your v of t function that's stored under y1. Any questions there? Okay, let's look at a Riemann sums problem. This is page 8. All right, page 7. My bad, page 7. So with Riemann sums, we're doing an approximation of integrals, of depth integrals, and we know depth integrals have this connection with area, right? And with area, we're essentially we're starting with something that's one-dimensional and getting to two-dimensional, and we're multiplying, in this case, width and height. So it says, so here's the important key point. When you're applying or approximating a calculus procedure, derivative integrals, your units of measure will change, right? We know that if we're dividing by something, it'll be a rate of change. So it could be meters per second, or it could be change in temperature per day. But if we're doing integral, our units are also changing in the sense that now we're not only multiplying the numbers together, you're also multiplying your units together. And when you multiply your units together, what you start with is going to change. Okay. So let's look at this table here. So this table tells us the ounces per minute that is added to the cup from the coffee maker. So at 0 minutes, there's no water entering in. 1 minute in, it's coming out at a pretty fast rate, 5.1, well, relative to the other numbers, coming out at a pretty fast rate of 5.1 ounces per minute. 3 minutes in is slowing down a little bit, 4.2 ounces per minute. 3.3. By the time it gets to the 9th minute, it's down to a drip, 1.2 ounces per minute. And then 10, it picks up a little bit, 2.3 ounces per minute. So the idea is that, let's read this problem here. The hot water is dripping through a coffee maker, filling a large cup with coffee. The rate that water in the cup is changing from 0 to 10 is given as a differentiable function, where t is measured in minutes. Selected values, sorry, I meant to say selected values of C of t measured in ounces per minute are given in the table. So interpret the meaning of C prime of 6 and indicate the units of measure. So if C of t is measured in ounces per minute, then C prime is going to turn into what? Yeah, ounces per minute squared. So C prime of 6 tells us the rate at which water being added is increasing or decreasing. So it tells us that at the 6 minutes is the rate at which water is coming out, is it increasing or decreasing? So if you're going to tell, you probably tell it's decreasing, right? I mean, water is still coming out, dripping through a coffee maker, but it looks like it's transitioning down to a slower drip, right? So this is basically at the second derivative level, because C of t is already at the derivative level. So anytime you're asking to write out what how to interpret the second derivative, you're always going to want to include these words here. The rate is increasing or decreasing. Either the rate is increasing or rate is decreasing. Here, we don't know enough information yet, but this is the way that AP exam wants to see that you understand the second derivative. So we don't want to say rate of a rate. That's not clear enough. And we don't want to just say, oh, the rate is changing at units per second squared. That also may not earn full credit. And I also see some students, they want to use the word acceleration because we're used to seeing velocity acceleration as particle motion. So acceleration doesn't really fit this context as well. So the wording that you want to use to indicate to the grader that you understand this is a second derivative, it's rate of a rate, but instead of saying that, you want to say the rate is increasing or the rate is decreasing. In this case, we're probably expecting the rate to be decreasing because 4.2, 3.3, 1.2, right? The rates, the ounces per minute, the rate is decreasing potentially. So it says approximate C prime of 6 and indicate the units of measure. So it says approximates. We don't have enough information to find the derivative, but we can do slope, and we can choose any of these 3 points to find our slope. So I'll choose the last 2 here. I'll do 1.2 minus 3.3 over 9 minus 6. So C prime of 6 is approximately the rate of change from this 3.3 to 1.2. And just like what we suspected, our rate is decreasing, right? It's water still coming out, but it's kind of slowing down to a drip. And then our units of measure, now we can say ounces per minute squared. Okay, part C, interpret the meaning of the depth integral of C of t dt and indicate the units of measure. So we're basically accumulating all these together. So if we know that in the first minute, it's 5.1 ounces per minute, and then 4.2 and 3.3, 1.2 and 2.3, if we add all these together, if we find the area under this, then what information are we going to get? If we accumulate all these ounces per minute. Is the unit still going to change? Is the unit still going to remain as ounces per minute? Or if we do the integral on top of the C of t? Or if it changes, what will it change to be? Just ounces. Good. So this, if we know how much water is coming out per minute, then we should be able to know how much water gets added in that time period, right? Or how much water or coffee gets added to the cup in that time period. So also, you can think of it this way. Integral from 1 to 10 of lowercase c of t would become uppercase c of t minus uppercase c of 1. So if you think about, this is how much water is in the cup at 10 minutes. This is how much water in the cup at 1 minute. And this indicates how much water has been added to the cup in this time period, in this 9-minute period, in ounces. So anytime that you are taking the integral, whether you're just approximating or you're doing a depth integral, our natural tendency is we just want to say, oh, this is just an accumulation of ounces per minute. But your units will change, just like how if you're finding the derivative, your units changed, right? You went from ounces per minute squared. So here you're going from ounces per minute back up to ounces. So this represents the change in the amount of coffee in the cup between the first and the 10th minute. It's displacement. It's how much of something has been added. Okay, part D, now it says use two middle rectangles to approximate the value. So now we can use Riemann sums. We can do what we did on the quiz, where we split up our region into two subintervals, and then we identify the width by subtracting the t values, and then we pick out the middle y value as our height. So here, 6 minus 1 is 5, so 5 times 4.2. And then 10 minus 6 is 4, 4 times 1.2. So our approximation is that over this time period from 1st and 10th minute, 25.8 ounces have been added to the cup because we're taking all these ounces per minute and we're accumulating them over the period of 9 minutes. Next up, approximate the average rate of water being added. So basically, we're just doing average value theorem. We're doing average value of this integral. So we'll do 1 over b minus a of that integral. We can still use the 25.8, just have to divide by 9. So now we're back to ounces per minute because the 25.8 is ounces, but we're dividing by 9 minutes. So ounces divided by minute. So our units is back to ounces per minute because we're dividing our area by the width and we end up with the height. So just want to kind of give you a heads up as to in terms of what your test will look like. So your test will just be 3 FRQs. And you'll see a derivative graph like page 2. You'll see a particle motion like page 6. And then you'll see a Riemann sums like page 7. So we're just over the next 2 days, we'll still kind of take time at the second half of class to just continue running through these different types. And I'll have help session tomorrow morning, Thursday morning, and Friday morning. If you want to come in, you have questions, you want to go over some more of these problems. Okay. Hi, come make your phones. Again, your homework is from the new unit, page 1 and 2.
I've got a few, like, so we started texting, like, we made the invite ourselves to this. Yeah. We're gonna have those actually. Also, we have friends who want to try to customize it. Anybody else? Yeah. Yeah. I guess that's just. To me, that's not. Yeah.
Thank you. Thanks for doing this. I'm working. Appreciate it.
We actually got to show you Bruce.
Yes. Great, thank you.
So can I take this like the first 1%?
You want to do that for me? You can, but you can change your mind. So just want to give you the option. Okay.